Good afternoon, everyone. Thank you for making time for our webinar, Distribution Systems, Managing Chloramination and Nitrification Risks. This webinar is brought to you jointly by USA Blue Book and the Hach Company. I'm John Wilson, Lab Product Manager with USA Blue Book, and I'll be the moderator for today's presentation. We've got an hour scheduled for today's webinar. If you've got questions during the presentation, please use the Q&A button at the top of the page to post them. All questions will be posted anonymously, and we've left plenty of time at the end of the presentation to get to all of those questions. The webinar is being recorded, and all attendees will receive a copy of today's presentation. Our presenter today is Mike Green, a sales development manager at the Hach Company. Mike is bringing 2 decades of practical experience helping water professionals with solutions to their monitor and testing challenges. He's bringing that to our webinar. Mike, please go ahead.
Good afternoon. I'm Mike, and thank you to USA Blue Book for putting this together. If you run a chloraminated system, you already know it behaves like a living thing. It drifts, it gets worse in August, and it rarely tells you it's in trouble until a customer does. That's what the next hour is about. What's actually happening in the water, why it can go sideways, and how you can catch it early. Everything here is written for people who do this work, small systems included, not for a complex central lab facility. We're going to build this in layers. Disinfection first, then chlorination, then chloramination, since each one rests on the one before it. And it'll ask the same 3 questions every time. What is it? Why should you care? And how do you actually measure it? That last question, that's where we'll spend the back half. Now, before we start, what is that suite of tests a chloraminated system depends on? Every one of them has to be right, and most of them have to be right today, not next week. Please hold on to that thought. We'll come back to how long that panel takes you and what those parameters are. A quick bit of background. Hach started in 1947 in Ames, Iowa. And water analysis has been the entire business ever since. It's the whole company, not one product line inside a larger one. Lab, portable, online, and the tested methods behind them. The methods and the instruments work together, proven chemistry and instruments built to run it accurately every time. What the founders were after was simplification. Nothing should get between an analyst and consistent, accurate results. Today, that's a global operation, part of Veralto's water quality group with associates, labs, and field service teams on every continent, serving about 1 million water quality professionals. So the support behind whatever you buy is local to you, no matter where you operate. And now let's talk briefly on how disinfection got to where it is. What I like about this timeline is that it isn't really a chemistry story, but a public health story. Chlorine sat around for over 50 years before anyone used it to save a life. In the 1830s, London was dumping it in sewers because the city smelled. Nobody connected it to disease until germ theory. Once they did connect it, the change was fast. And in terms of numbers, in 1900, typhoid fever ran about 100 cases per 100,000 people in this country. Jersey City chlorinated first in 1908, and the rest of the country followed within a decade. By 1920, that rate had dropped to 33.8. Today, it's 0.1, and about 3/4 of those are picked up traveling abroad. I'd like to highlight this. The steep part of that fall happened before antibiotics and before any vaccination program at scale. What moved the line was treating the water. CDC puts drinking water treatment on its list of the 10 great public health achievements of the 20th century, next to vaccination. That's the work you all do, and nobody ever tends to get thanked for it because a disease that stopped happening doesn't make the news. Then in 1993, Milwaukee, Cryptosporidium, 400,000 people sick. That outbreak is why CT rules exist. CT is concentration times contact time. The point of it is that adding disinfectant was never enough. You have to prove that you held the right amount for long enough. And on the next slide, what does disinfection actually mean? Disinfection isn't sterilization. What we're doing is inactivating the things that make our water unsafe for consumption. Bacteria, viruses, and protozoa like Giardia and Cryptosporidium. And it isn't just a chemical. It's a process, physical, biological, and chemical steps working together. Chlorine is the workhorse of that process. And the thing worth remembering is that it's really two species in a tug of war, hypochlorous acid and the hypochlorite ion. Hypochlorous acid is the one that does most of the work for us. Now, which decides that split? pH. Hold on to that. It comes back to us later today. And the job doesn't end at the plant. Primary inactivation happens there, certainly. The residual is what protects the water all the way through to the distribution system to the tap. Now, none of this counts unless you can show it. Residual and CT, that's concentration times contact time, are how you prove it. And they're the basis of most of the rules we work under. And looking at the numbers, 0.2 milligrams per liter entering distribution as a minimum, 4 as the ceiling. These two limits come from two different risks. The floor is there because the residual has to survive all the way out to the last house on the system. So 0.2 isn't a number you aim at, it's what still has to be left at the far end. And the ceiling is there because more chlorine means more byproducts and more taste and odor complaints. That's why you can't fix a weak end of the system by simply dosing harder at the plant. The real job is managing how fast that residual disappears between here and there. Let's focus on chlorine for a quick moment. Now, we want to be fair to chlorine here. It's strong, it's fast, it's relatively cheap, and it is still the primary disinfectant for most of the country. Nothing on this slide is an argument against using it. But look at the disadvantages together rather than one at a time. Every one of them gets worse the further the water travels. Disinfection byproducts build with contact time. The residual fades with water age, and taste complaints come from the far end of town, not the plant. And with respect to that ceiling, you can't simply dose your way out of a fading residual because 4.0 is a compliance limit. That's the corner utilities find themselves in, which we'll see next is exactly why systems start adding ammonia. So, chloramination. It's chlorine plus a little ammonia, and what you get is monochloramine, a milder disinfectant that lasts a lot longer. And that's the trade-off. Simply, you give up some punch to buy some reach. If your problem is disinfection byproducts at the end of the system or complaints from the far side of town, that may be a trade worth making. But having a look at the disadvantages, it only works if the dose is right. Roughly 4 or 5 to 1 chlorine to ammonia. If that ratio is left to drift, the leftover ammonia becomes food, which is the whole nitrification story that we'll get to. One practical thing people forget, monochloramine has to be removed before the water reaches dialysis equipment and before it reaches aquatic life of any kind. Fish, amphibians, reptiles, and the invertebrates at the bottom of the food chain are all sensitive to it. And unlike free chlorine, it doesn't just sit out overnight. It has to be actively removed. Worth getting ahead of because these are the calls that will come in.
Mike, I want to break in here real quick and put up a quick poll for our attendees to get a better idea of, now that you've explained chloramination, what their experience is with chloraminated water systems. Reply to the poll question with little to no experience, occasional exposure, or very limited involvement, or if you regularly work with chloraminated systems. I'll give everyone a minute or so to clock in with that. And it's looking like close to half of our attendees regularly work with chloraminated systems.
Well, that's great. Thanks, everyone, for your participation there. When we talk disinfection, it involves chlorine almost all of the time, and may involve ammonia as well. Now, talking about the formation of chloramines, here's the part that surprises people. You don't add ammonia and simply get monochloramine. You add ammonia and get a mixture, and the ratio, pH, temperature, and contact time decide which one wins. Monochloramine is the one you want. Dichloramine and trichloramine are what you get when conditions drift, and they're the ones people can taste and smell. Small dosing changes move that balance, which is really the argument for everything in the second half of this presentation. If the reaction has to be actively controlled, it has to be actively measured. And on the next slide, the curve shows us what this looks like in practice. Now, not to get too technical, what's shown here is the chlorine measured against chlorine added. And the reason this isn't a straight line is the whole concept. One thing to state up front, this curve assumes that ammonia is in the water, either naturally occurring or deliberately fed, as in the chloramination we just covered. Without ammonia, you don't get this shape. The chlorine still gets consumed by organics, iron, manganese, sulfide, and everything else exerting demand, but there's no combined residual forming, so there's no hump and no breakpoint. You just see demand satisfied and then free chlorine climbing away. At the bottom left of this curve, we're adding chlorine and getting nothing back. That's demand. The water is essentially eating it. Then it climbs, and that climb is chlorine combining with that ammonia to form monochloramine. That's the zone that you want to live in. And then it turns over between zone 1 and 2. Past the peak, the chlorine you add starts destroying the chloramines you already made. You're spending money to lose residual. And on the next slide, we'll look at the full breakpoint curve. Now, this may look familiar. The 3 zones are shown here once again. In zone 1 or region 1, demand is satisfied and monochloramine is building. This is where we want to be. Zone 2, and you've gone past the hump. Dichloramine and trichloramine form, and the residual actually falls. Taste and odor complaints usually occur right here. Then in region 3, past breakpoint, now you're making free chlorine again. Now here's the part I'd like to underline. A plant drifting to the right on this curve is adding more chemical and getting less protection. If someone tells you they keep raising the dose and the residual keeps dropping, this curve really helps explain the answer. And this leads us into why a handful of parameters have to be watched together. So let's talk about what we actually need to watch. And we want to frame these as early warning signs, not as a checklist of tests to run. Monochloramine first, because it isn't an indicator, it is the disinfectant. It's the barrier itself all the way to somebody's tap. Too little, and you're not measuring a process problem, you're measuring the absence of protection. Think biofilm, coliforms, and violations that can follow. Free ammonia is how you know your ratio is honest. That leftover ammonia is fuel sitting in the pipe, waiting for something to burn or consume it. And something always will. That's the trigger for the whole nitrification cycle we'll walk through shortly. Total chlorine is your compliance number. And with monochloramine present, it's the one you report, not free chlorine. But it's also a diagnostic. If total chlorine and monochloramine start separating, that gap is your residual breaking down into something you don't want. pH is the quiet one. And I was just speaking with a customer yesterday regarding the impact that their particular system has with pH, as it can fluctuate. It doesn't cause a problem by itself. It decides how stable everything else is, whether your chemistry stays on monochloramine or slides towards dichloramine. Let pH drift and you get taste and odor complaints and a residual that decays faster. It often looks like a dosing problem when it isn't, which is why it belongs on the testing panel. And on the next slide, nitrite and nitrate, evidence that it's already going wrong. Now, these two work differently from the others. Nitrite and nitrate aren't dials you turn. They're evidence, the fingerprints of nitrification already underway. Rising nitrite is one of the earliest things you'll see, and it exerts chlorine demand of its own. So the residual loss feeds on itself. Now, stepping back and looking at all five, monochloramine, free ammonia, and total chlorine and pH are things you control. Nitrite and nitrate are things that happen to you when the first four get away. That's why you measure them together. Any one alone is a snapshot. Together, they're a diagnosis. And on the next slides, let's look at nitrification proper. Nitrification is the thing that keeps chloramination operators up at night. So let's give it its own section. All right, picture the conditions. It's August, the tank on the edge of town turns over slowly, and nobody has called to complain. That's exactly when this starts. Monochloramine breaks down a little on its own and releases ammonia. Bacteria consume the ammonia and make nitrite. More bacteria turn nitrite into nitrate, and the nitrite itself eats more of your residual on the way. The reason it's nasty is that it feeds itself. Every pass through the cycle leaves you with less protection than the one before, and less protection means more biofilm, which drives the whole thing faster still. And it doesn't announce itself, it just erodes. And once nitrification takes place, there are a lot of operational challenges to turn it back. And out of the group here, there may be some of you who are chasing a residual at a dead end right now. Now, on the next slide, the good news is that the numbers move early. Right, so here's the encouraging part. The numbers change long before the phone rings. Free ammonia falling, nitrite ticking up, monochloramine slipping, even dissolved oxygen dropping. That's your window. That's when it's still a dosing adjustment. By the time total chlorine is falling and plate counts are up, you're not managing anymore, you're responding, flushing, retreating, and explaining. So the distinction I'd like to take from this slide isn't early versus late indicators. It's whether you find out from your data or from your customers. And on the next slide, there's a hard regulatory line under all of this. Now, this is genuinely a health limit, not an aesthetic one. Nitrite at 1, nitrate at 10 milligrams per liter. And what's behind those numbers is that both interfere with the blood's ability to carry oxygen. Infants under 6 months are the particularly vulnerable group, what people still call blue baby syndrome. And I'll take volunteers to offer the correct pronunciation of the medical term for this. So the bottom line on an uncontrolled event isn't just that you lost residual. The nitrite and nitrate produced along the way carry their own health-based limits. So losing control of the residual can also put you in violation. And on the next slide, we'll bring it back to the operator in the field. Everything we've covered assumes that somebody actually runs the tests. So let's talk about what that's really like. In a small system, it might be 1 or 2 people, a truck, and a list. Reagents, glassware, consumables, a meter for pH, and colorimeters for everything else. in addition to the space that's required. Get one thing wrong and you're repeating tests, driving back out. That's what the left side is shown here. Hours that none of us have, and blind spots that come from testing the bare minimum because the full panel takes too long. And the right side is what it looks like when the testing is quick and repeatable. You test more often, so you're looking at trends instead of single readings, and the decisions get easier. Just as important, you get to make them earlier, catching a residual sliding or nitrite ticking up while it's still a small adjustment to the feed instead of a system-wide problem. That's the difference between a tweak and a flush and recover. And to take it further, it's a difference between staying in compliance and explaining a violation. So, how do we perform these tests successfully? We know which tests matter, and we know what it costs to get them wrong. The question is how you actually get them right on a Tuesday in the field with the time you've got.
And Mike, this is another spot where I'd like to jump in with another poll for our audience. This one involves asking where they typically do their testing. And select all that apply. Is your water quality testing typically done through process analyzers online and continuously? If you're doing your testing on site in the field where you're collecting your samples, are your samples being tested internally in your in-house laboratory, or are you sending your samples out to a third-party lab for analysis?
Fantastic. Yeah, it's a great question.
Majority of our attendees look like they do most of their testing out in the field, on site, where the samples are collected.
Well, great. And that comes as no surprise. Let's dive into this then. On the left, we have listed every control parameter we've talked about, matched to how you'd measure it 3 different ways: bench, field, and continuously or online. The lab column is straightforward, and the online column is where a lot of utilities are heading. But the thing I'd like you to note the most is this middle column. This is where most of today's day-to-day burden falls, as you demonstrated with the poll results, because that's the testing you're doing out in the system at the moment you actually have to make the call and make decisions. And on the next slide, let's talk more about that middle column. Well, shown here is the SL1000 or PPA. And rather than walk through specs, I'd rather frame it as 3 things customers often tell us. It takes too long, the numbers don't agree with one another, and there's too much gear to carry and keep track of, calibrated, and serviced. These are common things we discuss with customers regularly using some legacy apparatus and tools. Now, as a little break here, let's start a live test so that it's running in the background. I have with me here an SL1000, and I'm going to initiate a test for free and total chlorine with a sample that I have taken that's present here on my desk. So just as the image in front of you shows, I'm going to place the device into the water sample tray, and it's asked me to remove it from the sample. All I need to do now is set it on the desk beside me, and it will let me know when it's done. So faster, more consistent, simpler. We'll talk to each one. First, speed. Without the use of a device like this, 30+ minutes means an operator may run this panel once. Same time, same day of the week, one reading. That's a snapshot. Under 10 minutes, on the other hand, means we can run it before a change and after it and actually see what moved. And I'd like to point out that the numbers we have shown on this slide represent the reaction time. We haven't even considered here the prep time gathering the materials, and setup, which make these two numbers drift even further from each other. And that's the real change from reporting a number to understanding a trend. Everything we said about catching nitrification early depends on testing often enough to see the slope. And on the next slide, speed only counts if you can trust the number. And we often get agreement on the entries on this slide because everyone joining us here today has likely had two results that didn't agree and no way to tell which one was right. Look down the left column. Scratched cells, mixing by hand, forgetting to zero, maybe the wrong volume, temperature. None of those are somebody being careless. They're just what happens when a method has 15 manual steps and it's cold out, or the phone rings mid-test. The right column is the answer, and the one I'd point at is the last row. 10 plus readings per test with the outliers thrown out instead of the single reading you'd get by hand. And on the next slide, there's simply less to carry. This one's less scientific and more about the realities in the field. 1 meter for colorimetric and electrochemistry. Everything in one case with reagents and probes. Fewer parts to lose, fewer things to forget on the bench back at the plant. And next, let's talk the chemistry that it covers. Rather than walk this line by line, the point is that the whole chloramination and nitrification panel is on one instrument, and several of the instrument methods are EPA approved, notably chlorine, copper, and fluoride. If your question is whether it covers your reporting requirements, this is a great slide to capture. One more thing worth saying about this chemistry, it's built to refuse a bad reading rather than hand you a wrong one. Now, speaking of readings, the SL1000 has informed me that the results are ready. So now I've had a sample sitting out for a little while here, so I am expecting some changes, but I've just obtained a live reading of 0.1 free chlorine and 0.57 total chlorine. Now, this sample was taken from an appliance that I have here where I was doing a little bit of cleaning with chlorine. So these aren't necessarily results that are going to be representative of a utility, but I wanted to demonstrate how quickly and easily we can obtain these two results in a trustworthy fashion. So talking about the trust of the measurement, noisy readings or odd kinetics, this will stop and give you a message. If one of these chem keys, shown here on the screen in detail, is not sealed or seated properly, the instrument will give you a message regarding aspiration or leak error, not a false number. It also flags a used chem key, an expired lot, and a sample that is too warm. An error you can fix beats an incorrect result you would have otherwise reported. And shown here on the slide are the chem key reagent ranges from the Hawk datasheet, with a footnote shown here as well. Well, how about some helpful hints? And certainly not exhaustive, but these are the things that we would tell an operator over the phone. First, we might stop thinking of it as one species. Monochloramine, dichloramine, free chlorine, and ammonia are all in there at once. You're managing a balance, not a single number. Second, the window. pH around 8.2 to 8.3. Water cooler rather than warmer. You often can't change temperature, but knowing how far off you are tells you how hard the chemistry is working against you. And third, this is one that catches people. Don't trust a DPD free chlorine reading when monochloramine is present. the combined chlorine species interferes. Total chlorine is what you report. If you genuinely need free chlorine, use a method that doesn't suffer that interference, such as indophenol. And on the next slide, one item before we get into an opportunity for some questions. Quick practical note. There's a promotion on the SL1000 and its sibling, the 250, running through the end of August. If any of what we've covered sounded like your system or a system that you might be working in soon, the thing to do is to talk to your USA Blue Book representative before the deadline, and we'll be around once we wrap up if you'd like to talk through your system. And next, we're happy to move to questions for a few minutes.
Thank you, Mike. Yes, there have been a few questions that have been posted during the presentation. First one here. Can I use a free chlorine test to determine if my chloramination system is working?
Well, that's a good question. And a free chlorine measurement is part of the story. And when we look back to the curve that was shown that shows ammonia, chlorine, monochloramine all together, free chlorine can be an indicator that can tell us that we have moved past our breakpoint and are generating free chlorine. But it is not the only parameter that's required to help maintain a chloraminated system successfully.
All right, got it. What's the first parameter we should check if we suspect a nitrification event is starting in our distribution system?
Well, certainly the presence of free ammonia, which acts as the food for the bacteria that will cause the nitrification, is a leading indicator. So free ammonia is critical for that. Now, if you have the ability to measure nitrite as well, an early onset of nitrite tells you that nitrification process is starting to happen. The nitrite occurs before the nitrate, so it can act as an early indicator as well.
Thanks. Next question. What importance is there to total ammonia measurement compared to free ammonia?
Well, that's a good one too. So when we talk about total ammonia, we can frame that with reference to total chlorine. And the ratio that utilities are looking to achieve between 4 and 5 to 1 represent total chlorine versus total ammonia represented as nitrogen. So that total ammonia value will help calculate what that ratio is and if that ratio is correct for our system. So it is a key parameter for us to capture.
Thank you. What's a good testing frequency to catch trouble early?
Well, this is a great question, and we get asked questions like this quite often. So the way I might think of answering that is that if you have the ability to perform frequent tests quickly that you can trust, you can get into a habit of doing frequent testing to determine how much your system is changing during that time period. Once you have determined with more data points that your system has the stability that you were hoping for, you might choose to expand the measurement frequency to save time or save reagent with that knowledge that you already have. But without knowing the granular data in the background between grab sample points, you just don't know what's happening. So we do want to investigate that to get our finger on the pulse of the system.
Yeah, I can see where that one can be a very site-specific type of answer to something like that. The last question that has come through was one that also occurred to me during your presentation. The question is, you mentioned dissolved oxygen. Should I be monitoring that like I do ammonia and pH?
Well, I'll say this as a manufacturer of analytical testing solutions, we encourage folks to do as much testing as is possible. In the real world, dissolved oxygen can be used as a useful measurement to help us round out that entire picture of what's happening with respect to nitrification in the system. It's not necessarily a core parameter that we hear customers are measuring all the time. But as you look at how ammonia changes to nitrite and nitrate, those are oxidation steps, and it turns out oxygen gets utilized in that process. So measuring dissolved oxygen with simply the ease of placing a probe onto the SL1000 would allow you to have that extra data point for even more confidence in how your system may be changing.
Looks like a couple more have come in just very quickly. This one asks, you discussed the effect of excess ammonia on chloramination. Can you discuss the lack of enough ammonia?
Well, sure. And if we look back at the curve that was shown, too much ammonia versus our chlorine means that we have that excess ammonia that can lead to nitrification. Now, on the flip side, not enough ammonia means that we haven't been able to convert as much of our chlorine to monochloramine as we would have liked. And so that means that our dosing ratio is off a little bit. We're a little bit heavy on chlorine, which can have its own effects, as well as for those that are looking to optimize chemical usage. We don't have the ammonia available there to react with it. We're simply not going to be establishing that formation percentage that we're hoping to achieve. And some utilities reference that they want to have more than, say, 90% formation of total chlorine to monochloramine. So it would fall into those areas, I think.
Okay. And then looks like one last question. Are there certain parameters that need to be set if mono is higher than total?
Right. So if we're talking total chlorine and monochloramine, so those, if we're doing well, those two numbers should track fairly well together, and we may have a little bit of a gap between them. Now, typically, the mono number should not be higher than the total chlorine number. But some testing can show this artifact. And so when things like this happen, it may be important to look back through the testing methods and have a look to see if one or both of those parameters could be off a little bit. If we have a calibration that's off a little bit, because those end up being numbers that don't really make sense to have. So it would be a good opportunity to raise a flag and take a deeper look at all those tests.
All right, thanks. That looks like all of the questions.
Well, great. And thank you for the interaction. Now, these are some closing points worth carrying with you. Chlorine that is used to disinfect water with a lot of organic matter in it makes disinfection byproducts. Those are regulated. Monochloramine largely solves that, but hands you a more complicated reaction to run. You can't control that reaction with one measurement. It takes a combination, both in the plant and out in the distribution system. And be proactive. Everything we looked at today moves early. The whole premise is deciding whether you want to find out from your data or from a phone call. And here's what we consider to be the no-brainer part. Everything I've just asked you to stay ahead of, the ratio, the free ammonia, the nitrite that shows up first, is the whole panel on one handheld device out where the problem actually lives. No reagents to measure, no method to remember. You open a chem key, run the sample, and you get an answer you can act on before you leave the site. And if something isn't right, it tells you that instead of handing you a number you would have otherwise trusted. Now, none of that replaces your judgment. What it does, it takes the friction out of testing often. And testing often is the entire difference between catching nitrification early and chasing it. So be proactive, test more, and let the data make the call. Thank you all for your time today.